So let us discuss now another decoder. Previous session I discussed about the decoder block diagram, the decoder operation, and we have discussed 3 to 8 decoder, and we have discussed 74138 decoder IC. So how we are going to get the output based on the control inputs and additional signals, enable signals. So now let us discuss one more type of decoder. So it's another application, I can say. Whenever I give BCD inputs, as you know the BCD inputs, so we are going to generate now the code, the input code over here is BCD, and I am going to generate the decimal out of it. So let us discuss what is BCD to decimal decoder. So BCD decoder have 4 inputs and 10 outputs. So now you can think over here, if I give 4 inputs, you will be having 16 combinations, but now here I am going to take only 10 outputs here, since it is BCD, binary coded decimal. The 4-bit BCD input is decoded to activate one of these 10 outputs. So we have 10 outputs here. So it accepts 4 active high inputs and provides 10 independent active low outputs. So this is what the BCD to decimal decoder functionality. So you can see the truth table here. We have BCD inputs. Even though I have, as I said, even though I have 4 control signals, I am going to generate 16 combinations. Even though we have 16 combinations, we are going to consider here only 10, since we treat this as BCD. BCD represents 0 to 9. So the inputs are from 0 to 9. So I will not be considering this, will be not using this inputs. After 9, these are treated as invalid inputs. So whenever I give input to the decoder 0 0 0, so my particular output, since as I said it's active low, the first output is low, the rest all are high. So at a time only one output is active here. So now I am generating decimal coding here. So my inputs are BCD 0, so the output is 0 here. So similarly 1, my output is this active low at this pin. So we have 9 outputs, we have 4 inputs. So 4 decimal inputs with 9 combinations, I am going to generate 4 different decimal outputs. So you can just see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I am generating 10 different outputs based on this BCD inputs. So we call this as BCD to decimal decoder. The other inputs are treated as invalid inputs. So the next example what I am going to teach, or an application where I can use my decoders, you can just see this is BCD to 7-segment decoder. So what exactly is BCD to 7-segment? You can just see here, there is a segments over here. All this red line represents one segment. Each segments are named as A, B, C, D, E, F and G. So totally we have 7 segments. How many segments? 7 segments. Yeah. So each of these segments are arranged in the number 8 fashion. You can just see here, it looks like number 8. So this is one of the popular method for displaying. I think all of our LED displays digital displays you can get this pattern. So you can just see over here, this is nothing but 7 segments from A to G. We named this as from A to G. So it can display this 7 segment, we call it as a single unit. So this is one unit, each unit has 7 segments. So each unit able to display the characters. I can display the characters from 0 to 9 as well. I can, instead of displaying 10, I can display the hexa character from A to F. So I can make this particular segments on. So this is termed as one single 7 segment unit. So all this 7 segments can be turned on or off. Each segment is of one LED. So that is nothing but light emitting diode. So how exactly this is done? So basically it's an light emitting diode. So how this operates? So each segment, as I discussed in the previous, each segments is nothing but one LED. So these are light emitting diodes. These are the diodes. These segments will be on whenever I give supply or power to the particular LED. So these segments will be light and others will be dark, so that you can get a desired character pattern can be generated. So the segment pattern that are used to display the various digits, you can just see here, there are various patterns. So to turn on this particular segment, the LED will be on. So for example, you can see, to display character 6, I need to turn on A. So B is not there. C, I require C, D, E, F and G. So only except one segment, all other segments I should turn on to display this particular number, that is 6. So similarly I can display from 0 to 9. So based on the what pattern you want to display, so that particular segment will be made high or turn on. So you can just see here, for 1, B and C segments are used. So like this we can generate a pattern using this 7 segment. So this display, as I discussed, that display unit, so we have two types of 7 segment LED displays. So one is called common anode, the other comes in the configuration common cathode. We have two configurations. So let us discuss what exactly is common anode and what is common cathode. So you can just see, in common anode configuration you have this 7 segments, this becomes one unit. So we have 7 segments over here, each segments are named as A, B, C, D, E, F, G, and all these 7 segments, additionally this is on a display, there is one more unit, one more dot is there, right? So we have named this, each segments are connected to the pins A, B, C, D, E, F, G, and this is a dot pin. So and this unit is connected to supply. So in common anode configuration, anode of all the LEDs are tied to the positive of the power supply. So this is the symbol of LED. So each segment represents one LED. So there are 7 segments, you will be having 7 LEDs. The symbol of LED you can just see over here. So this represents a triangle and a dash, and this is nothing but LED, emission, light. So it's emitting light. So this is nothing but anode and this line represents cathode. So this side it is cathode, the other side it is anode. So common anode configuration, all the LEDs, that is 7 LEDs, plus this is an additional to turn on this dot. all these anodes are tied together as you see, and it is connected to power supply 5 volts VCC. So this is nothing but common anode configuration. So your display works in common anode configuration. In common cathode configuration, the second method or connecting this segments is nothing but common anode configuration. In common cathode configuration, the cathode of all the LEDs are tied together and it is connected to ground. So these are all connected to ground. This minus 5 volt represents ground. So A, B, C, D, E, F, G, H is connected to anode. All the cathodes are connected to ground. So these are the two configurations that can be connected in order to display this particular unit. So now let us discuss using this 7-segment display unit. I am going to design a BCD to 7-segment display unit. So now let us discuss how exactly this 7-segment display operates. You can just see this is a separate unit. This is 7-segment LED display. We call it as LED display. So in common cathode configuration, we have used the cathode of all LEDs are tied together as we have shown in the previous. Now we have the inputs BCD. So BCD is nothing but A, B, C, D. So these are the inputs I am going to connect. As you know, 4 inputs. BCD, it's connected to 7-segment output. So the output will be 7 segments. So all these outputs are named as A, B, C, D, E, F and G. So BCD 2, it is 7 segments. So we have 7 outputs here, 4 inputs here. So output of this decoder is connected to the input of this 7-segment display. So you can see all these segments A, B, C, D, E, F, G are internally connected to these pins. So LED A, for example, LED A is connected to this pin A. So we have as such all lines here. So this particular line A of this 7-segment, this pin is connected to the output of the decoder, that is the first output, that is A. So this is how we make the connection for BCD to 7-segment display. You can just see over here, as I discussed, we have 4 inputs. So any combinations I can give. So in these combinations, we have taken an example 0, 0, 0, 1, where A is MSB, D is LSB. Suppose 0, 0, 0, 1. So all my outputs 0, 0, 0, 1 means I should light, my output should be 1. The code should be 1. To make this output display unit to display number 1, so this particular segments B and C should be on. So whenever I give 0, 0, 1, then B and C segments will be on. So these B and C outputs becomes logic 1. So 0, 0, 1 if I give, I need to display 1 at the display unit. So B and C will be, the output of B and C will be logic 1, the rest all it will be 0. So this B and C is connected to the display unit. So the particular segments B and C will be on. So at the output side, you can see on the LED 7-segment display, you can see the LEDs B and C. Out of 7 segments, only 2 segments will be on. So now let us take an example how BCD to 7-segment display can be realized using truth table. So let us discuss with a truth table explanation. So as I said, we have 4 inputs. So these are binary inputs. So these are binary inputs. So I am going to generate here BCD. Since I am talking about BCD, so I will be writing only 0 to 9 combinations. So I will be writing so we have 0 0 1 2 3 4, this is 5 and 6 7 8 and 9. So I have 4 inputs. So I have designed 9 combinations. I have given inputs 9 combinations. These are my binary inputs, and my decoder output will be, as I discussed, we have outputs, we have 7 outputs A, B, C, D, E, F and G. So these are connected to, these are decoder outputs, these are inputs and these are outputs. Output of the decoder is once again connected to 7-segment display unit. This is an unit which is connected to the output of decoder. So we have a decoder here. The input to the decoder is 4 bits. So output of the decoder are 7 bits. All these 7 bits are connected to the 7-segment display output. So now let us discuss this, how exactly you are going to get this outputs. So we have 0 0 0. Whenever I want to display 0, as you know, we have unit like this. So in this unit, this represents A, B, C, D, E, F and G. Suppose I want to display 0, then what are the LEDs that should be on? So what are the segments that should be on? We have 7 segments. It is in turn, it is nothing but LED, right? So we have 7 segments, it is nothing but 7 LEDs. So we have 7 segments over here. Suppose I want to turn, right, 0, my output should be 0. Then what are the segments I should make on and what are the segments that I should make off? So the first input is 0. So 0 means, so suppose I want to display 0. So 0 is displayed like this on the 7 segment. You can just see the segments are A, B, C, D, E and F, where G is not on. This particular segment should be off. So I should see only A, B, C, D, E, F to get this pattern, that is 0 pattern. Segment on means it is logic 1. The segment off means it is logic 0. So to get a desired pattern, I should make on. The rest I should make off. So now I am going to write for 0. For 0, except this G, all other, except this G, all other segments are on. So I will write 0, which is off, right, and I will write 1 for all segments, that is from A to F, all segments are on except G. Similarly, so my output will be like this now. Next is, so that is nothing but 0. Next is 1. I need to display 1 on the segment. So to display 1 on this unit, so I need to turn on this particular unit. So only B and C will be on, the rest will be off. So I am going to write here B and C on, the rest will be off. So this particular segments B and C is logic 1, the rest all are logic 0. Similarly, I am going to display 2. So 2 is displayed in this fashion. So in this 2, only these two segments are off, that is F and C. So F and C is off, the rest all is on. So you can just see for 2, it is A is on, B is on, and then C is not on, D, E, then F and G. So next 3. For 3, so for 3 it is once again like this. So for 3, how I am going to write the pattern? For 3 it is 1, 1, 1, 1 and 0, 0, 1. So particularly E and F is off here, E and F. This is for 3. So next for 4. So for 4 it is off, on, 0. I am going to write 4 like this. So for 4 it is 0, 1, 1, 0, then 0, 1. So particular segments you can take A. So A is off, B, then C, then D is off, then E is off, then F, G is on. So this is how I am going to write for from 0 to 9. This is 6, 7, 8, 9. So let us fill this truth table now. This is for 4, this is for 5. So 5 it is 1, 0, 1, 0, 1, 1, 0, 1, 1. And for 6 it is 1, 0, 1, 1, 1, 1, 1. So for 7, 1, 1, 1. So for 8, all the segments should be on. You can just see for 8, all 7 segments should be on. So that's why it is logic 1, since my display pattern is of 8 shape. So you can just see here, this is, so this is the truth table of BCD to 7 segment display. So finally I can generate out of this combinations, I can generate 9 combinations, I can generate 9 different outputs using 7 segment display. So I can display numbers 0 to 9, as well I can display characters from A to F. So these are the decoder outputs, these are the decoder inputs. So this is one of the application of decoder. So we'll start with the next combinational circuit, which is an opposite to decoder, that is encoder. So what is an encoder? It's a combinational logic circuit that performs a reverse operation of decoder. So even as we discussed earlier, decoders, now it is the reverse. It is nothing but it has got n inputs and n outputs, and encoder accepts an active level on one of these inputs, which represents a particular digit, such as it can be a decimal or an octal, and it converts to a particular coded output. So the output can be in terms of BCD or binary. So it accepts a particular input and generates the coded output. So encoders are basically devices to encode various symbols and as well as alphabetic characters. So process of converting from symbols or numbers to a coded format is called as encoding. So now let us discuss the truth table and operation of encoder. You can just see here the block diagram of encoder. In this we have n input lines, m output lines. So these n input lines, so this is a reverse operation. As we discussed in decoder, we add the reverse. Number of output lines were more there. Here it is, the input lines are more, the output lines are less here. So you can just see here, one of the input lines is I, then a particular code is generated. If out of these lines, if my least significant bit input is I, the rest all are low, I will be generating the particular code that is 0, 0. So this is a code from one input. So in the second case, if I make the I0, I2, I3 zeros and I1 as logic 1, my particular code will be generated as 0 and 1. Similarly, here I2, I3. So for I2, you can just see the code generated is 1 and 0. Here the code is 1 and 1. So you will be generating codes particular at the output lines. So we have 8 to 3 binary decoder design. So 8 to 3 in the sense we have 8 input lines, 3 output lines. It is just reverse of decoder. We had 3 to 8 decoder. So now we have 8 to 3 encoder. So encoder is the reverse of the decoder. So usually in communication circuits, they use combinations of decoder and encoder and the transmitter as well as receiver side. You can just see here 8 inputs, 0 to 7. So at a time, one of the input is I and we will be generating a particular code. So this we have 3 outputs. So 3 outputs for a particular input, we will be getting a code. So you can just see here, out of this 7 lines, this line is I. So I will be getting the code 0, 0. If D1 line is I will be getting 0, 0, 1 code. If D2 line is I will be getting 0, 1, 3 code. Similarly, I will be getting for all 7 combinations different codes. So these codes I can write the equations for each of these outputs. So outputs A0, A1, A2. For A0 will be, the equation will be A0 is equal to D1 plus D3 plus D5 plus D7. So this is nothing but when this particular A0 is I, whenever you get an output from D1, we can input from D1. So input from D3, input from D5, similarly input from D7. You can just see 1, 2, 3, 4. So under A0, in A0, you can just see this 4 times the output is I. So when you are going to get this output high, whenever that particular input signal is I. So you can just see here D1, D3. So A0 will be I whenever D1, D3, D5, D7 is logic 1. Similarly, I am going to write for A1. So A1 also has 1, 2, 3 and 4. If you see this output A1, I am going to generate 1, 2, 3 and 4 terms. So that is nothing but D2 here, then coming over here D3, then here it is D6 and D7. So D2, D3, D6 and D7. So A1 is equal to this inputs. A1 will be having I output whenever we give this inputs. So A2. So when we are going to get A2 as I. So whenever we have D4, D5, D6 and D7. So we have generated here 3 equations since we have 3 outputs. So let us design 4:2 priority encoder. So what do you mean by priority encoder? So priority is nothing but if more than one input is active, then which one has to be considered or which one has to be redirected to the output side. So that is called as priority encoder. So if more than one input is active, then the higher order input has got more priority over the lower order input. So always the higher value is encoded on the output side. So this is what the priority encoder is. So if more than one input is active, then we will be considering the higher order. So we will be indicating this whether the output is valid or not valid. There is an indicator, we call it as a valid indicator. It is represented by V, which is included to indicate whether or not the output is valid. So when I say V is valid, when I say V is invalid. So output is invalid when no inputs are active. When nothing is given to the input side, we say output is invalid. So then your V bit becomes 0. So output is valid when at least one of the, at least it can be more than one also. So we will consider the priority. So at least one input is active. So then my V output will be 1. So since I am talking about 4:2 priority encoder, we will be having 4 inputs and 2 outputs. I am considering additional output indicator, that is V over here. So in the truth table, you will be having 4 inputs D3, D2, D1, D0, and I will be having 2 outputs plus additional output, we call it as valid output. So we have, suppose all of my inputs are 0 as indicated, all of my inputs are 0. So you can see that no matter whatever may be the output, it's invalid. So your V output will become 0. It indicates no inputs are active. Suppose the first input is active, you can just see here. So your outputs are 0, 0, then V will be indicating 1. Similarly, the second input, the code will be 0, 1. The first input, the code will be 0, 0. If there is a second input coming on the second line, then the code will be 0, 1. If the input is coming from third line, no matter whatever may be the inputs over here, even though you get 1 here, so you may get 1 or 0, you may get 2 simultaneously, but the priority is given for higher order. Suppose here D1 is coming, means this is logic 1, even D0 is logic 1, all D2, D1 are logic 1, means all 3 inputs are simultaneously active. Then we are going to consider here the higher order bit. So the higher order is redirected. So higher order is D2. So my output will be 1, 0. So here in this case also, if my D0 is 1 also, my output will be D1 only. So you can see this D1 has got highest priority compared to D0. So my output will be 0 and 1. D2 has got highest priority over D1 and D0. even though you are getting inputs, only D2 is considered. So that's why your output is 1 and 0. So you can see all of this valid outputs are valid outputs. You are getting logic 1 over here. So considering the last row, all D2, D1, D0, no matter either it is logic 1 or 0, D3 has got highest priority over this 3. So my output will be, the code will be 1 1. For 0 D0, my output is 0 0. For D1, my code is 0 1. D2, my code is 1 0. For D3, my code is 1 1. So I am going to generate a particular code whenever I apply the inputs. Even though I apply more than one inputs, higher order input will be considered and particular bits will be I. So let us design this 4:2 priority encoder. So in this you can see the inputs. So we have 4 inputs, as I discussed, 2 outputs and 1 valid output. So we have filled this truth table. So considering no inputs, D0 input, both D1 and D0, no matter whatever may be the D0, D1 has got highest priority. No matter whatever D1 and D0, D2 has got highest priority. No matter what is D2, D1 and D0, D3 has got highest priority. Considering this, we have filled this output. So D0 represents 0 0, D1 represents 1, D2 represents 2, the code, D3 represents 3. So 0 represents invalid 1. So now I am going to write a truth table here, K map here. So the K map has got 4 inputs, D3, D2, D1, D0. You can just see D3, D2, D1, 4 variable K map. I am entering all these inputs. Then I am going to draw equation from this K map. So I will be writing 2 K maps here, considering A0 and A1. So for A0, I am going to fill this. So fill this table. For 0 0 0 it is X, for 0 0 0 it is X. Next for 0 0 0 1 it is 0 0 0. For 0 0 0 1, that is 0 0 0 1, it is 0. I am not considering 0. So I am considering wherever there is 1, I will be considering. So the rest all out of 16 combinations, right? Since I have taken only this much combinations, the rest all is treated as logic 1. You can just see these 2 ones are combined here. So this is not used. So we can do grouping here, considering all logic 1. So this one is considered, 2 groupings are done. This is one group and these 2 another group. From this I am going to generate an equation A0. So A0 is nothing but, if you take this 2 rows common, it is D3 is common, both are common, that is 1 and 1, that is D3. So if I take common, nothing is common this way. So horizontal way, row wise this is common, column wise nothing is common, so you will end up with only D3. So coming over here, these 2 grouping, so these 2 are common and these 2 it is D2, D2 complement. So D1, D2 complement. So I am going to generate K map. So like this grouping, I am going to generate an equation from this K map. Similarly for A1, I filled this and then done grouping. So we will get this equation, D2 plus D3. So this is common, it is D3, this 2 is common, these 2 rows common, it will be D3, these 2 rows common, it will be D2. So so once you can see, if I fill similarly, I will get equation, I get the equation of V whenever it is logic high, it is D0 plus D1 plus D2 plus D3. D0, D1, D2, D3. Since all 4 lines are high, so I have used this equation. So finally we have got 3 equations, A0, A1 and V. So out of this equation I am drawing a logic circuit of 4:2 priority encoder. So this priority encoder has got D3, D2, D1 input, and we have in the equation there is a complement for D2, so I have used an AND gate complement. For A0 I have got one OR gate and 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 NOT. So D3 is connected and we have D2 complement and D1 through AND gate, and these two are connected to OR gate, will be getting A0. So coming here A1, we have equation D2 plus D3. So directly I'll be connecting D3, D2. So you will be generating A1, output A1. So we have a single OR gate, no AND gate here. So coming to V. So how do I generate this V? It is nothing but directly I am connecting D0, D1, D2 and D3. It is 1, 2, 3, 4, 4 input OR gate. So this is a circuit of 4:2 priority encoder. So let us summarize what exactly we have discussed. So let me discuss what we have completed in this session. We have discussed about decoder, Bcd to decimal decoder, which has got 4 inputs and 10 outputs. So out of 16 combinations, I am just going to take only 0 to 9 combinations since I need to generate 10 outputs. So the 4-bit Bcd input is decoded to activate one of the 10 outputs. It accepts active I input and provides 10 independent active low outputs. I think you can just see over here the truth table, and we have discussed about 7-segment display unit, how the each display is being turned on or off. So we have 7 segments named as A to G, and then each segments are nothing but LED. It is a light emitting diode. So this light emitting diode can be made on or off by particular configuration. We have 2 configurations, common anode, common cathode. So in common anode configurations, we have connected all anodes of the LEDs together to the positive terminal, that is VCC. All cathodes are connected to the particular segments A, B, C, D, E, F, G. So totally we have a single unit which the pattern looks like 8. Common cathode, we connect all cathodes to or tied together and it is connected to ground. So we can connect the decoder output to 7-segment display unit in order to display the digits 0 to 9. As well I can display A to F hexadecimal characters. So based on the inputs, I can turn on particular segments. I can display a particular character. So for example, to display BC, I can make this only 2 segments on, the rest all off. So like that I can display all 9 outputs. So the patterns look as a truth table. So I can display from 0 to 9, the particular segments will be on, the rest will be off to generate a pattern. We discussed about encoder, which is just a reverse of decoder. So it accepts n inputs and m outputs. So accepts an active level on one of its inputs and represents a digit such as decimal or octal and converts it into coded output. So it can be devised to encode various symbols and characters. we have discussed 8:3 binary decoder encoder design, and we have generated equations, output equations. Then we have a priority encoder. When one or more inputs are active, then which has to be considered. So we give preference over here as higher order bit. So higher order input as given priority, and it is over the lower order input, and the particular output will be generated. To check whether the output is valid or not, invalid, so we are going to introduce one more bit called V. So based on that, we are designing 4:2 priority encoder. So we have written K maps for the outputs A1 and A2 by taking into consideration 4 variable K map. Out of 4 variable K map, so we have entered the other terms as don't care, and then we have grouped. So finally we have arrived with the equation, and the valid bit is taken directly. The logic ones are ORed D0, D1, D2, D3, and we have generated a circuit diagram. So finally I conclude this session by the discussion of the operation of decoders. You have analyzed the operation of decoders, 7-segment decoders, encoders, and you will be able to design the priority encoders. Thank you.